Okay, so we're back for the last portion. What we're going to discuss right now is this idea of the Nyquist frequency. Now, where I left you was with this image. And this image here is basically the idea of a line profile that is acquired across a uniform image. And that uniform image would be a flood source. So the idea is that you would think that a uniform image means exactly that. It's a uniform image, that I have a certain amount of activity spread across my field of view, and I should have all of my line profile, all of my counts that are detected within my line of sight across each profile slice should be equal, because we have a flat field source. It's an ideal, it's a uniform and perfectly efficient source. However, in reality, the number of counts coming off of that flat uniform source are not perfectly equal. There are highs and there are lows in this line profile. And that is because no matter what you do with this row of pixels acquiring activity, you are going to always have high frequency noise and low frequency background. So you are going to have these sharp peaks no matter what. So the idea of the Nyquist frequency, it's a mathematic formula, problem, theorem, that basically says that no matter what, you are always going to have half the number of peaks as the total number of pixels in your matrix. So in simple English, if I have a 64 by 64 size matrix, I can only have 32 maximum peaks and 32 minimum peaks. So I can only ever have half the number of my total. As far as why to remember that, it is what it is. You have to basically remember that at any point that this point in a frequency is called the Nyquist frequency. You're only ever going to have the same number. You will always have the same number of peaks as you have valleys. So if you think of a sorry, if you think, I'm trying to get my slide here. If you think of a okay, so no matter what, if I have frequency and amplitude and amplitude and frequency, no matter what, if I have up and down and up and down, oops, all right, not very good with this. But if I'm counting 1, 2, 3, 4, 5, 6, 7, 8, 9, I have nine green peaks. Okay. And that means that I should have 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 green lows, right? Low. And peak. High. Okay. The same with no matter how many, the green is more, the green is a higher frequency than the red. So I have 1, 2, 3, 4, 5, 6. I have 6 highs. And 1, 2, 3, 4, 5, 6 lows, right? Okay. So in the Nyquist frequency, I can never have more highs than I have lows, and I can never have more lows than I can have highs. If you translate that across in your number of pixels in your matrix, you can only ever have highs hitting so many pixels as you have lows hitting the other pixels. So go back to our image. And here we are at the end. So the Nyquist frequency is basically just that we have the same number, we have half as many highs as we have our total, and half as many lows as we have for our total. So for the past presentations, I have covered reconstruction, sinograms, slice profiles, the difference between filter back projection and iterative reconstruction, as well as the Fourier transform, which transforms your image into waveforms, which again helps us with the understanding of sinograms, and sinograms helps us with the understanding of waveforms, and the idea that the Nyquist frequency is also based in this idea of waveforms. We can only have half as many high frequencies as we have total frequency, high and low. Okay, any more questions, please reach out. Thank you very much. We'll be back with the next lecture that is discussing filters. Thank you very much.